Hello dear students, let us solve some numerical problems related to the refraction through plane surfaces. At first, let us review the related formulas. Refractive index is given by Snell's law according to mu is equal to sin I upon sin R, where I is the angle of incidence and R is the angle of refraction. Mu2 is the refractive index of second medium and mu1 is the refractive index of first medium. Also, refractive index is defined as the ratio of the velocity of light in air or vacuum to the velocity of light in the given medium, and also mu is equal to the ratio of real depth to the apparent depth. Here c is velocity of light, here c is velocity of light in air or vacuum having value this much, and v is the velocity of light in the given medium. If c is critical angle, then sin c is equal to the ratio of mu of rarer medium to mu of denser medium. First question is, a transparent cube of 12 centimeter age contains a small air bubble. Its apparent depth when viewed through one face is 6 centimeter and when viewed through opposite face is 2 centimeter. What is the actual distance of the bubble from first face? Solution to question 1. Suppose this is the face of rectangular cube. Total its age is 12 cm. Suppose this is the position of air bubble. When it is viewed from end P, it appears to be 6 centimeter, and when viewed through end Q, it appears to be 2 centimeter. So, given from face P, A1 is 6 centimeter apparent depth, and from face Q apparent distance is A2 2 centimeter. Now we have to find the actual position of bubble from P. From first face P. Now, refractive index is given as the ratio of real depth upon apparent depth. Refractive index is given as mu is equal to real depth upon apparent depth. Suppose real depth is T1, this distance is T1, and this distance is T2. So real distance is T1 and apparent distance is A1, this one. This is T1 upon 6. Suppose equation 1, and from face Q, mu will be equal to real depth T2 upon apparent depth A2. Therefore, T2 can be written as 12 minus T1. 12 minus T1 upon A2 is 6. A2 is 2 centimeter. Equation 2. Equating 1 equating 1 and 2, we get equating equations 1 and 2, we get T1 upon 6 is equal to 12 minus T1 upon 2, 2, 3 is T1 upon 6 is equal to 12 minus T1 upon 2. Therefore, T1 will be equal to 36 minus 3T1, or 4T1 will be equal to 36. Therefore, T1 will be equal to 36 upon 4 means 9 cm. So, the air bubble will be at distance 9 cm from first face. Question number 2. Second question is, an optical fiber with refractive index 1.72 is surrounded with glass coating of refractive index 1.5. Find the critical angle. So, solution to question number 2. Here we have mu denser is equal to 1.72 and mu rarer 1.5. Therefore, sin C will be equal to mu rarer upon mu denser 1.5 upon 1.72. C will be equal to sin inverse of 1.5 upon 1.72, which gives 67.45 degree. Question number 3. What is the apparent position of an object below a rectangular glass slab of refractive index 1.45 and thickness 0.06 meter, above which a layer of water 0.04 meter thick is placed? Now, solution to question number 3. Here given this is glass slab of refractive index mu glass is equal to 1.45, and above this glass slab a layer of water which is 0.04 meter thick. This is T2 and this is T1. T1 is 0.06 meter thickness of glass and T2 is 0.04 meter thickness of water. So we have to find the apparent position of this object, which is placed below the glass slab. Suppose apparent position A, apparent position of object of solution. We know refractive index mu is the ratio of real depth and apparent depth that is T upon A. Therefore, A will be equal to T upon mu. Therefore, in glass, A1 will be equal to T1 upon mu glass, and in water, A2 will be equal to T2 upon mu water. Therefore, total apparent depth A will be equal to A1 plus A2. A1 is T1 upon mu g and A2 is T2 upon mu water. T1 is 0.06 upon mu g is 1.45 and T2 is 0.04 upon mu water is 1.33. So, we get total apparent depth as 0.071 meter below the top. Means when this object is viewed from this point, it will appear to this depth. Next, question number 4. A microscope is focused on the scratch on the bottom of a beaker. Turpentine, which is a liquid, is poured into beaker to a depth of 4 centimeter, and it is found that the microscope has to be raised 1.25 centimeter to bring the scratch into focus. Find the refractive index of turpentine. So, solution to question 4. Here given, suppose this is beaker and this is the scratch which is acting as object. To see this scratch, microscope is at this position. microscope is at position M1 without liquid, and when the beaker is filled with turpentine liquid to a height T is equal to 4 cm. This is beaker and this is turpentine liquid. Then this microscope has to be raised to this position M2 to refocus on the scratch. This distance is given to be 1.25 cm. This distance. Then we have to find the refractive index of liquid. Now, when liquid is filled in the beaker, this object will be slightly raised to this point, and to focus on this point, the microscope has to be raised through the same distance. Therefore, mu will be equal to real depth upon apparent depth real depth is 4 centimeter and apparent depth is 4 minus this much, means 4 minus 1.25 centimeter, which gives centimeter cancels out, and we get refractive index as 1.45. So, the refractive index of turpentine liquid will be 1.45. How long will light take to travel 500 meter in water? Velocity of light in vacuum is 3 into 10 to power 8 meter per second, and the refractive index of water is given to be 1.33. Solution to question 5. Given refractive index of water is 1.33. Velocity of light in vacuum is 3 into 10 to power 8 meter per second. Distance is 500 meter. Distance in water. We have to find time. Time taken by light to move 500 meter in water. If v is the velocity of light in water, then refractive index mu will be equal to, refractive index of water will be equal to C upon V. Therefore, V will be equal to C upon mu water. C is 3 into 10 to power 8 meter per second and mu is 1.33. So, V comes to be 2.256 into 10 to power 8 meter per second. Now velocity is the ratio of distance upon time. Therefore, time taken will be equal to d upon b. D is 500 meter and b is 2.256 into 10 to minus 10 to power 8, which gives 2.22 into 10 to minus 6 second, and as we know 10 to minus 6 is known as micro, therefore it can be written as 2.22 microsecond. Next question number 7. Light from a luminous point from the lower face of a glass slab 2 centimeter thick strikes the upper face and totally reflected rays outline a circle 3.2 centimeter radius. Circle of 3.2 centimeter radius at the lower face. What is the refractive index of glass? Solution here given. Suppose this is glass slab and its thickness is 2 centimeter. This is luminous point. This is the luminous point. Light ray moving from this point to this point at almost critical angle is totally internally reflected. So we can take this nearly equal to critical angle. Similarly, this is nearly equal to critical angle and totally internally reflected rays. Similarly, this is totally reflected ray. These two totally internally reflected rays outline a circle of radius 3.2 centimeter. This is 3.2 centimeter. This is 3.2 centimeter. Therefore, this will be 1.6 cm and 1.6 cm midpoint. Now, from figure, tan C will be equal to perpendicular upon base. The perpendicular is 1.6 cm and base is 2 cm. So, C will be equal to tan inverse 0.8 is equal to 38.66 degree. Therefore, mu will be equal to, or therefore sin C will be equal to mu rarer upon mu denser. Mu rarer is air here 1 and mu denser is mu air upon mu glass. Mu air is 1 and mu glass is to be found out. Therefore, mu of glass will be equal to 1 upon sin C